continue with another example problem. This example problem reads, refrigerant 134A is throttled from the saturated liquid state at 700 kPa to a pressure of 160 kPa. Determine the temperature drop during this process and the final specific volume of the refrigerant. So here's the schematic. We have the pressure going in at 700 kPa. We have it at saturated liquid. It comes out at 160 kPa. So let's go ahead and start by drawing some assumptions. One, we're going to assume this to be a steady flow problem, steady state problem. Two, we're going to assume that the change in kinetic and potential energy of the fluid is zero. And since this is such a small area, this valve, I'm going to assume that there's no heat flow. And I'm also going to assume that there's no work being done. So, like all of the other problems, we'll go ahead, write out our first law in its most compact rate form. Energy in by heat, mass, and work minus energy out by heat, mass, and work equals the change in energy of the system. Rate change of energy of the system is zero since the state of the system doesn't change. That leaves all energy in has to equal all energy out. So that would be energy in by heat plus energy in by work plus the sum of all the mass flow rates in, and that would be including the enthalpy, kinetic energy, and potential energy of that fluid going in. That would equal all heat out plus all work out plus the sum of all of my mass energy out multiplied by the enthalpy, the kinetic energy, and the potential energy. Now, let's go ahead and cross out the terms that don't belong. There's no heat or work in or out. That leaves only mass flow, and there's one mass inflow and one mass outflow, so that means that the mass flow rates cancel out on both sides of the equation. And we're assuming no change in kinetic or potential energy. So that results in the enthalpy going in equaling the enthalpy going out. And that is why we call a throttling device an isenthalpic device, because the enthalpy is constant. All right, so let's go ahead and solve for what the problem is asking for, which is the change in temperature in and out. So state one is the inlet. So we have the pressure going in at 700 kilopascals, and we know that it's a saturated liquid, right? So the quality is zero. That gives me a temperature of 26.7 degrees Celsius. Now, I need two properties to evaluate all other properties because this is a refrigerant. It is not an ideal gas. It is refrigerant. So we need two properties to get all the other properties, right? So at the exit, they give us the pressure, but we don't know anything else. But I do know that according to my first law analysis, this device is an isenthalpic device. So what I can do is, knowing the enthalpy for state one, I can equate that to the enthalpy at state two. And I can go ahead and use those two properties to find the exit temperature of the refrigerant. And also it asks me for the specific volume of the fluid when it exits the valve. So and the other thing it's asking for is the delta T, right? So that would be the temperature out minus the temperature in. We end up with a total change or drop in temperature of 42 degrees, 42.3 degrees Celsius. So that makes sense because what a throttling device is meant to do is reduce the temperature, significantly reduce the temperature of the refrigerant so that the refrigerant's ready to remove heat from a space inside of a building or in a refrigerator. So we'll talk more about that in a later chapter, but basically this throttling device resulted in a significant drop of temperature with it being an isenthalpic device.